Hello guys, welcome on Tesla Adventures. In this video, we'll start with torque, and in this video particularly, we'll study all the basics of torque and some examples of torque. So starting with the question that what is a torque? So torque is an ability of a force to change the state of rotational motion of a body, which means that if a body is at rest, then torque can initiate a rotational motion state in that body, or if a body is already in the state of rotational motion, then torque is a quantity which can bring that body to permanently rest. So torque is a ability of a force to change the state of rotational motion of a body. So in simpler words, torque is a physical quantity that can either rotate a body and it can stop a rotating body. So this is a torque. Now how torque is calculated? Imagine a lever arm and a ball connected to that, and there is a hinge about which this ball can rotate. So if we apply some force on this ball in this direction, in the tangential direction of its circular motion, then this force will produce a torque which will rotate this ball about this hinge, and that torque would be equal to the product of this force and the distance of the point at which force is applied from the hinge. So this is the torque, which is the product of force and this distance. Now torque is a vector quantity, and the direction of torque can be calculated by Fleming's right hand rule. You can curl your right hand fingers in the direction of rotation of the body, and the thumb, which is pointing straight, will represent the direction of torque acting on that body. So in this case, if you curl your fingers like that with your thumb opening straight, then your thumb would be pointing in the upward direction, and that is the direction of the torque acting on this ball. Now this torque is actually the movement of force about some point or some axis. Now what is movement? Movement of anything is actually its product with the distance from the axis of rotation. So torque is actually the movement of force about some point or some axis. Now is torque a vector quantity? Now we have already discussed that torque is a vector quantity and its direction can be calculated by Fleming's right hand screw rule. And obviously this torque is represented by the cross product of R and F, where R is the distance of that point of application of force from the hinge or the point about which we are calculating the torque, and F is the force which is producing the torque. So according to Fleming's right hand screw rule, if we curl our fingers of our right hand starting from R towards F, then the thumb will point in the direction of torque. And we know that any quantity which is the result of the vector product of any two quantities would be perpendicular to the plane containing those two quantities. So we can also say that this torque will also be perpendicular to the plane containing R and F. Now let me tell you the direction of this torque with an example. That let's suppose there is a point O and a force F is being applied at this point like that. So this is the force F, and this is the R vector, which is the position vector of this point. Now this is the point on which the force is applied, and we have to calculate the torque of this force about this point O. So the torque would be in the direction of r cross with f. So this object would rotate like that, and therefore the torque acting on this object about this point O would be in the direction which is coming out of this plane of the board. So this is the direction of torque. Now what is the physical significance of the torque? You must have seen that this is a wrench, and the wrench has a long handle. So to open a screw, we mostly prefer to apply the force at a distance which is greater from this part of the wrench. Because let us see that, let's suppose if the distance of this part is RA from point A, and the distance of this part is RB from point B, then the torque tau, if let's suppose FA and FB are equal, so if we apply same forces on these two different points, then the torque acting due to at point A would be FA into RA, which is F into RA. Now the torque B, tau B, would be FB into RB, which is F into RB. So you can see that RB is greater than RA, therefore torque of B would be greater than torque of A, which means that despite of applying equal forces at two different points, the torque is produced much more in the case when this force is applied at point B, which is a point which is far away from this point O. So it is very important that to rotate any object, the force is required as well as torque is required. So greater would be the torque, and greater would be the possibility that that object can start rotating. Now this is another example in which we are writing the torque on wrench by the formula force into lever arm. Now lever arm is the distance of this point of application of force, perpendicular distance from the hinge. So you can see that in this case the force is perpendicular to the wrench, therefore the distance, perpendicular distance of the force from the hinge would be this one, R, and therefore the torque would be F into R. So this torque would be maximum also. And in this second case, if the force is applied like that, and this is the angle theta, then the perpendicular distance of this hinge from this force would be this one, and this distance would be r sine theta. So the torque would be F into r sine theta. So tau would be equal to F into r sine theta. Now as this wrench will rotate, this angle theta would decrease, and therefore the torque will decrease, and a moment will come when this theta would be tending to 0. Therefore torque at this case would be almost 0. Now in this case you can see that there is a point P on which a force F is applied, and there is a point Q about which we have to find out the torque of this force. Now the distance of P from Q is R, and we know that the torque would be equal to force into perpendicular distance from the point Q. The Q is the point about which we have to calculate the torque. So this is F into R perpendicular. Now R perpendicular would be R sine theta. So this is R sine theta. Actually, first of all, we have to draw the line of action of force, and then we have to draw a perpendicular to this line of action from this point, which is also called as hinge or the axis of rotation. So this is R sine theta. So the torque will be F R sine theta. Now in this, to get a good feeling about torque, let us see some examples which are based on calculation of torque. So in this question, there is a particle of mass m which is released in vertical plane from a point P, from this position P, and at x is equal to x naught on the x-axis, it falls vertically along the y-axis like that. Now we have to find out the torque tau acting on the particle at the time t about the origin. Now obviously this particle is falling freely, so acceleration in free fall is always equal to g, and therefore the distance, this distance, let's suppose it is x, or let's suppose it is y, so this distance y would be equal to half gt square. So this is the distance y. Now we have to find out the torque of this force mg about point O. So what we'll do, we'll make the line of action of force, and we'll draw a perpendicular from point O to the line of action of force. So this perpendicular, R perpendicular, is OP, and it is equal to x naught. So the force, the torque would be equal to the force mg into R perpendicular. So torque would be equal to mg, and R perpendicular is equal to x naught. So this is the torque which is acting on this object about point O. Now let's move on the next question. A particle is having a mass m and it is projected with some velocity v0 from a point P, like that, and it is on the horizontal ground making an angle theta with the horizontal. We have to find out the torque about the point of projection acting on the particle when it is at maximum height. Now we know that at maximum height the velocity of this particle would be v0 cos theta, and the force acting on this particle would be mg. Now we have to find out the torque of this mg about point P. So let us draw the line of action of mg, and let us draw the perpendicular from P. So the perpendicular from P on mg would be this one, and this distance is r by 2, which is half of the range. So the torque of this mg about point P will be mg into r by 2, and the direction sense of rotation of the torque would be like that. You can see that this would rotate this object about point P in this sense, which is clockwise sense. So this is clockwise, and the direction would be z cap, which is k cap. So torque will be mg into r by 2 into k cap with a negative sign, because direction would be in minus k cap direction. Now we know that the range is equal to u square sine 2 theta by g. So the torque would be equal to minus mg into u square sine 2 theta by 2g. So this is with k cap. So torque would be equal to minus m u square sine 2 theta by 2 k cap.